Yeah, it's a great pleasure to moderate this session today. And as Igor already said, we have the two speakers today, just sort of general rules. If you would like to ask any questions, you can type them in the chat or just raise your virtual hand, and then I can unmute you and you can ask. And there will be an opportunity to ask some informal questions later after the presentations as well. And okay, so let's start with our first speaker. It's a great pleasure to have Haoyang here. She is currently a postdoctoral researcher at the Ecole Polytechnique. And prior to that, she was a machine learning and finance research associate at the Alan Turing Institute in the UK. And she has obtained her PhD from the University of California in Berkeley. And her research interests are in stochastic control, stochastic differential games and mean field games, and also in machine learning. And it's a great pleasure to have her speak today. And the topic will be feasibility and transferability of transfer learning, a mathematical framework. Please, Haoyang, the floor is yours. Thank you.
Thank you very much, Luigard, for the nice introduction. It's a really great pleasure to have me here at the seminar series. And today I'm going to share with you some of our recent study on the mathematical framework of transfer learning. This is a joint work with my current postdoc advisor, Professor Mathieu Zimbo, at SIAM Ecole Polytechnique, as well as my previous PhD advisor, Professor Xingguo from UC Berkeley, and one of her PhD students, Haoyang, who is of course graduating this year as well. And well, the idea of transfer learning has been around in application area in particular for quite some time. As you can see, the most commonly seen applications of transfer learning are concentrated within, for example, computer vision, as well as natural language processing. So here, this picture is actually a very high-level idea of one of the most successful large language models proposed by the team from Google. It's called BERT. So this is like two of the most celebrated areas for transfer learning and application. And in recent years, we have seen the progress of transfer learning being migrated to deal with, for example, medical data and financial data. So why do people want to apply transfer learning as opposed to directly solve a problem from scratch? So there are two primary reasons for people not trying to use the traditional machine learning approach to solve these type of problems. So the first one, the first challenge comes from the limitation on the training data. For example, for applications in biomedical fields, it will be, first of all, very hard and very expensive, and some ethical issues in terms of data collection. So it will be very scarce for the training data collection. And the second difficulty comes from the magnitude of some of the machine learning techniques. For example, for the large language models, we're talking about millions, sometimes billions of model parameters. So if we need to retrain the whole neural network from scratch, every time you want to realize some small improvement in the features or some functions, it will be very expensive in terms of time and resource consumption. So in that spirit, people turn to transfer knowledge that we have gained from solving some previously learned and relevant problems. So that's the high-level idea of a transfer learning. While we have seen transfer learning being applied to various specific scenarios in application, there are, however, some questions that people are constantly wondering about. For example, we want to know whether it's possible to have a more of a unified mathematical framework to theoretically study this notion of transfer learning, as opposed to tackle the problems one by one very individually. So this is the first question of how about the formulation of a mathematical framework for transfer learning. And the second one is that whether it will be possible to have a quantifiable way to make the judgmental call on whether it's beneficial to apply transfer learning versus learning from scratch. And if that is the case, whether that quantifiable way or quantifiable method can provide us with some idea on how to evaluate the performance of a transfer learning, things like that. So this is the second type of question on the when to apply transfer learning. And the third one would be, where should we look for the suitable relevant old problems so that we can learn the knowledge from them to tackle new problems. So that's the third problem about the question of where. So in order to address some of these problems, there have been some quite nice previous works in the theoretical aspects of transfer learning. So one major class of such theoretical works concentrate on a subclass of transfer learning problems, which is called the domain adaptation problems. For this type of problem, we usually have the same type of label or the output variables that we want to predict. The only thing that's changed is that maybe the input question is different from the old problems. So if we have gained quite some knowledge on the relation between the old input and the output, so now the only task that we need to accomplish is that we need to translate the new input data back to the old data so that we can make use of our previously learned knowledge on the relation between the input and output. So that's the sole motivation or the high-level idea of this type of domain adaptation problems. And as you probably can figure out from my previous description, that this is actually very in line with the idea of optimal transport. So back in 2016, there's a very nice paper written about an optimal transport perspective of domain adaptation. So that's like a very nice mathematical framework for this particular subclass of transfer learning. And another big chunk of existing works on the theory of transfer learning falls under the categories of all kinds of classification problems. So in some of these problems, they interpret this when problem into how should we bound the generalization errors. So they propose different score functions in order to do that. And also recently, these researchers proposed some information theoretical foundations in terms of how should we quantify the benefits of applying transfer learning for these specific type of classification problems with shared feature type of transfer learning technique. So these are some existing literatures in the theoretical studies of transfer learning. And so these existing works actually inspires us to see whether it's possible that we could provide a unified, first of all, provide a unified framework to include all these different scenarios. And based on that, we probably could propose some quantifiable methods to evaluate the performance of transfer learning accordingly. So that's what we're going to do. So before going into the mathematical details on the transfer learning per se, let's just first focus on more of a concentrated but general enough learning setup. That's the transfer learning for under a more or less a supervised learning setup. So for transfer learning, there are actually two problems. The old problems that we want to borrow the knowledge from, that's usually referred to as source tasks. So for supervised learning per se, we have input variables and output variables falling and under suitable spaces. And we have a set of admissible source models to map the input to the output variables. And this optimal source model, usually referred to as the pre-trained model in the machine learning literatures, that's actually the results of solving this source optimization problems. So these pre-trained model is the information that we would like to borrow from solving the source task. And we have, of course, new learning problems that we eventually would like to deal with. So that new problem is usually referred to as the target task. So we have a input-output counterpart for the target task, as well as the admissible, this should be target model, I'm sorry for the typo, target model sets. And here, this set of admissible models, AS and AT, they are with respect to particular problem settings. For instance, that should be for like neural network type of problems. That's usually restricted by the specific neural network structures that we choose in advance. So this target optimal model, FT star, is we eventually would like to construct. But instead of trying to solve this problem directly, we want to make use of this pre-trained model from the source task and see if we could build some relation between this pre-trained model and this optimal ultimate goal of this target of this transfer learning scheme. And in order to build a connection between this FS star and FT star, we propose this three-step approach to deal with that. So the first one is that we need to make some necessary adaptation on the input side. So there's like very practical reasons to do so. Theoretically, it's not necessary to have the same input spaces for both the source and target tasks. So in order to make use of that FS star, we sometimes need to make necessary adaptations on the input. So that's what we call the input transport mapping. So by applying this input transport mapping TX, we map input of the target input space back to the source input space so that we could proceed to step 2, that is to apply the trained model on the transformed input. But this intermediate product is sometimes it's not enough because as in the case of input, this output space might not match with the target output space as well. So we need the final steps of making an output transport mapping. So here we define this output transport mapping as some function that takes perhaps the target input variables as well as the intermediate product from the previous step and try to map them back to the target output space 1T. So this is a very common measure for many of the transfer learning applications, for instance, for image classification with the shared feature scenario. So we have the first few layers of the neural networks, which is called feature extractor modules. So that feature extractor module is directly copied from the source model. And then in order to eventually solve for the target model, we attach new classifier layers at the end of the feature extractor modules. That's exactly the role of this, the classifier layer is exactly the role of this output transport mapping here. But in a more generic scenario, we can see this output transport mapping at some operator that maps a YS valued function to a YT valued function. So that's a more generic definition, but for the sake of, for the ease of exposition, we will stick with this relatively easier way of definition for the output transform mapping here. So this is a summary of this three-step approach. So here is the hypothetical optimization problem for the target task. So if we want to solve it directly, that's exactly the way to go. But as I said before, sometimes we have limitations on the accessibility of data and or the obstacles on the complexity of the models. So instead, we want to go the other way around. So with the help of this pair of transport mappings for the input and outputs, respectively, we can make use of some pre-trained model FS star to complete the same objective. So this is exactly what I described on the transfer learning applied to the image classification scenario with the feature shared feature extractor module. So, so here, as we can see that this feature extractor module, which is in this particular case is constructed by the ResNet structure that's directly borrowed from solving some previously learned source task. And then we patch an input transport, which is a resize unit, and also a classifier layer at the end to complete the three-step approach. So, so as a summary, we can actually interpret this three-step approach of transfer learning as a new optimization problem. So this is actually exactly the optimization interpretation of transfer learning with respect to the pair of newly introduced transport mapping, as we said before. And of course, the first thing we need to verify is that this is actually a valid optimization problem. That is, we have to show that under suitable circumstances, there will be some optimal pair of transport mappings, TX star and TY stars, to solve this minimization problem. And here, the technical conditions are concerned with some proper choices of a loss function, LT, as well as some constraints on the set of possible output mapping here. And in reality, for most of the learning problems, the loss function have very nice convexity conditions, so that this compactness assumptions is sometimes is automatically satisfied. So for more, I don't think I have time to explain the proofs or the technical details of this results. You're very welcome to check our paper, which is available on arXiv right now. So we have, first of all, established this optimization interpretation of transfer learning and show that it's actually a valid optimization problem to be solved. And we actually can show that many of the previously mentioned transfer learning examples can be fitted into this optimization problem, including the domain adaptation and the image classification, as well as some large language models with this fine-tuning nature in the problem setting. So this is the story for the establishment for the mathematical framework of transfer learning through this optimization lens. And another nice product for having this framework is that we can accompany it with a quantifiable way to measure to measure the performance of the pair of transport mappings that we have introduced before, which is a very nice indication on the ultimate performance of this transfer learning technique. So as I said before, this transfer risk, as we say, we define here, it's actually in line with the optimization framework that I just introduced. So, so as we can see that we have this input and output transfer risk, as opposed to the pair of transport mappings in the mathematical framework. And each of these transfer risks will try to give us some idea on the performance of the respective transfer mappings. And after having this input and output transfer risk, we in the end have a bottom-up function C, which assumed to be a non-decreasing function with respect to both risks. And we have deliberately leave quite a bit of flexibility in terms of choosing the exact form of the C function, so that we can adapt this specific form of a transfer risk with respect to different test criteria. As an example, from a probabilistic point of view, we have some candidate choice on this on both of the input and output transfer risks, as well as the bottom-up function C. So usually, and as we can see in many of the previous work in terms of transferability, this transfer risk often takes the form of some distribution divergence between the ideal between the input between the source task and the transformed target task. Here we just choose a very simple linear combination of this two risk. This is one very simple particular form of transfer risk, and as I will show later on, there are of course other ways of choosing these C functions that's adapted to particular examples. And there's some remarks in terms of this transfer risk. First of all, it's regarding this involvement of this FT star. So a priori, we don't assume that we have direct access to this FT star function. So instead, heuristically, we can use this the distribution of the outputs, the output variable to approximate this law of this this optimal output of the target model. So with this replacement and also with under suitable conditions, we can actually guarantee that the error bound won't be too exaggerated. So now having a kind of a more relaxed and more easy to compute way of accessing this transfer risk, we can actually do the following. We can actually treat the computation of this transfer risk as a different optimization that's under a smaller scale. So first of all, for each choice of this input and output transfer mapping, we can compute for this transfer risk. And also, after a compute for each chosen pair, we can also do an optimization over a smaller class of this optimal transport pairs. So the reason is that with this heuristics, this computation of transfer risk is simple and direct. And with a smaller set of candidate transport mapping functions, actually this whole minimization problems over the transfer risks is much cheaper than doing a full-scale optimization of the transfer learning framework as we introduced previous slides. So the result is that the optimizers of this optimization problem over the transfer risk can actually serve as in some sense, a smarter initial configuration for the final transfer learning optimization problem in the end. So that's one of the benefits of having a second leg of in terms of helping us solve for the transfer learning problem in general. So this is one benefit of having a transfer risk. And of course, after introducing this transfer risk, we also established some nice theoretical properties for this transfer risk. For example, we show that it's actually continuous with respect to the source input and output distributions. So that is to avoid some undesirable situations where we have very minimal change in the source data, but then we have a very wild change in the performance of the transfer learning. That's not what we want. That's not what we wanted. So that's one of the properties for transfer risk. And then, as I said before, domain adaptation is actually tightly needed with the input transfer mapping within our proposed mathematical framework. And for that, we can show that actually zero input transfer risk is a necessary condition for a domain adaptation problem to actually work. And finally, in order to establish the relation between the transfer risk with the final performance of the transfer learning in general, we also show that the performance gap can be lower bounded by the transfer risk. So all these nice theoretical findings on transfer risks actually implies that we can use transfer risk to eliminate unwanted transfer learning schemes if the transfer risk is too high. And also, we can use transfer risk to rank and sort different source tasks if they are available. So that's actually a potential usage of this transfer risk. And as I introduced before, this transfer risk has a nice implication on the final performance of the transfer learning. So here are some numerical examples that can show the nice relation, the relevance between transfer risk and previously existed testing criteria. So here is once again the nice image classification problem over the data set of Office 31. So we have some commonly seen objects from offices that are collected from different web sources. The first one is collected from Amazon, the website, and the second type is from some digital camera data set, and the last one is collected from some webcam. So we perform a transfer learning test between each pairs, using one as source task and the others, some other one as a target task. So here we choose a particular import transfer risk as a Wasserschwann distance between the input and output, since we fixed the input transfer mapping here. And for the output transfer mapping, we also choose the Wasserschwann distance between the target variable, target output variable, and the distribution of the transfer learning product. So here, as we can see that among all these pairwise transfer learning schemes, there's like a very nice negative correlation between the accuracy and the transfer risk. So we can see that the lower the transfer risk is, the higher the accuracy will be in the end. So that shows a nice correlation of the relevance of the transfer risk that we have just proposed. So this is for the classification problem. And of course, for financial problems, we're also very interested in trying to apply our framework to that. But for portfolio management per se, it's a slightly different learning setting as we introduced before, since this is a rather unsupervised learning scenario as opposed to the supervised learning scenarios that we discussed before. So here you will see a slightly different learning structures, but the relevance of the transfer risk remains unchanged. So here for the portfolio management problem, we assume that we consider different assets with return vector R, and then we say that we have some candidate portfolio allocation vectors, and the goal is to optimize over the Sharpe ratio. And then the transfer learning idea here is that we use the source optimal allocation vector as a guidance, so that we don't want the target allocation vector to deviate too much from the pre-trained vector. So that's the whole idea of the transfer learning in this particular scenario. And then for transfer risk, we pay particular attention to the output risk here. And to measure the Wasserschwann distance between the source and target resulted total return. And in terms of application, we consider two different transfer scenarios. The first one is that what if we have some newly emerged markets? So we want to make use of what we have learned from a matured market and see if we could tackle similar problems in the newly emerged market. The second one is that how about the transfer learning among different frequencies? So that's the two transfer learning scenarios that we are interested in. So let me jump directly to the results. So here from the cross-continent transfer learning scenario, we can see that first of all, it's likely that the transfer learning would outperform direct learning if the transfer risk is low. That's happened to all of these four scenarios. And then we also see that for some cases, for example, the transfer from US market to European markets, it's the transfer learning probably performs better compare with a U.S. market transfer to the Brazil market. That's probably because there might be more connection between the U.S. and the European markets compared with the U.S. and other continents. And of course, here is a second scenario for the cross-frequency transfer. As we can see that we choose the relatively medium frequency as a target frequency and try to transfer from different frequency to this target frequency. And we also see a very nice negative correlation between the transfer risk and the final Sharpe ratio here. So that also suggests that the transfer risk that we have proposed has high relevance to the ideal testing or evaluation criteria for the specific problems that we're trying to solve. And here is the heat map between the transfer risk and Sharpe ratio. Here, I particularly want to point out that, first of all, if you see it more closely, we can see that both heat maps are not symmetric. So that means that in transfer learning, the direction of transfer learning, or which one we should treat as source text and which one we should treat as target, that direction matters. And also, and among this different frequencies, we can see that the 1 day frequency, so that this low frequency, is a bad source task, as opposed to 2 hours and 1 hour frequency. They are good candidates for the source task. So that's our kind of two examples in terms of applying what we have just proposed as a mathematical framework. In terms of applying it to some financial applications, as well as some traditionally popular CS applications. And as I pointed out from this observation, that is actually, there are quite a lot to be learned about transfer learning in general, especially from a theoretical perspective. And I guess I don't have time to discuss the details, and thank you very much for the attention.
Yeah, thank you very much for this very interesting presentation. Are there any comments or questions? I see one hand. Berkan, can you unmute yourself?
Hi, I apologize for this question. It reflects my own interests and my relative indifference to the current subject matter. Sure. But would this be could any of this be applied to singular control problems and mean field gain problems, as in your other recent works?
Oh, so that might be a little different. So currently I don't see a well-cooked problem formulation of transfer learning with connection to control problems. But well, in some sense, for example, we have control perspective in terms of understanding, let's say, deep learning. So in that sense, if we kind of put control together with deep learning, the training of deep neural network, and the application of a transfer learning. So that's kind of a long logical line, but I guess I could still smell some opportunities there, but I'm not sure. It will be very nice to see, to kind of explore that possibility.
Okay, thank you.
Thank you.
Thank you very much. Are there any other questions or comments? You can also type them in the chat if you like. If not, then there will be opportunity to discuss after the second talk as well. Yeah. So then maybe in the interest of time, we move on. But thank you very much again, Haoyang, for this very nice talk. So then we move on to our second speaker. Our second speaker is Stephan Eckstein. Stephan, can you already try to share your screen, please?
Yes.
Okay, so it's working nicely, very good. So thank you. Okay, so excellent. So Stephan is currently a postdoc in the Risk Lab group at ETH Zurich, and he works on topics related to robust finance, machine learning, and optimal transport. And prior to that, he was at the University of Hamburg as a postdoc, and he has obtained his PhD from the University of Constance. And it's a great pleasure now to have Stephan presenting his talk on numerical aspects of adapted optimal transport. So,
okay, yeah, thanks a lot for the introduction, and also, of course, thanks to all the organizers for giving me the opportunity to present this work here. So the very rough topic of this talk is adapted optimal transport. And so the overarching topic, I guess, are multi-period market models, because adapted optimal transport can be seen as a tool to study the structure of distributions of multi-period market models. And the work by my co-author, Goodman Pammer, and myself is in particular concerned with numerical aspects of this problem. So we basically have the goal of making this tool available for practical purposes. This is the outline for my talk. So first, I want to give you the motivation and introduce this concept of adapted optimal transport. Then I will show you some of our main results regarding numerical aspects of adapted optimal transport, among others, discretization, regularization, and a particular algorithm to solve the regularized problem. And finally, I will show you some numerical examples. So regarding adapted optimal transport, I want to first shortly recall the normal optimal transport problem. So in optimal transport, you have two distributions, mu and nu, which are Borel probability measures on RD. These are called the marginal distributions in the problem. And you have a cost function, which is a function from RD times RD to the positive reals, which we always assume to be continuous. And then the objective of optimal transport is to optimize over some measures pi, which I will come to in a second, the integrated cost of this cost function c integrated over this measure pi. And this measure pi is taken out of the set pi of mu and nu. And each measure pi out of the set is a measure on this product space RD times RD, where the marginal distribution on this first product space equals mu, and the marginal on the second product space equals nu. So we call this set pi of mu and nu the set of couplings between mu and nu. And this is visualized here. So if you have in D equals 1, two distributions, mu and nu, then these measures pi are the possible joint distributions, where the first marginal is mu and the second marginal is nu. And these joint distributions pi basically tell you how to transport this mass, which is sitting here at the locations of nu, towards nu. And of course, optimal transport has been around for quite some time, and it has found applications in many different areas, like operations research, physics, finance, machine learning. And I want to emphasize one particular instance of this problem, which arises if you choose the cost function c as a metric on RD, because then this optimal transport problem actually defines the Wasserstein distance, which is a metric on the space of probability measures with finite first moment. And in fact, it metrizes the topology of weak convergence together with convergence of the first moments. So now, of course, this talk is not concerned with this normal optimal transport problem, but instead we are interested in adapted optimal transport. So next, I want to motivate this concept of adapted optimal transport. So now let us consider two stochastic processes, two very simple stochastic processes, x and y. So now this dimension here of these marginal distributions is really considered as time. So here we have two distributions on two time steps, mu and nu. Let us first look at this process y distributed according to nu, which is just a two-step binomial model. So we start here at 0, and we either go up or down with probability 1/2. So at first glance, this model x here looks quite similar, but it's actually quite different. So here for this model x, we either start slightly above 0 or slightly below 0, and both with probability 1/2. And if we start slightly above 0, we deterministically go up. And if we start slightly below 0, we deterministically go down. So what I now want to emphasize is that these two models, in a sense of weak convergence, or in the sense of the Wasserstein distance, are actually very similar. So epsilon goes to 0, then these two models are basically the same. However, if you think of these models as really market models, so as distributions of some stock process, for instance, then they behave, of course, quite differently. So, of course, this process here on the right-hand side, this is a martingale, where this process here on the left-hand side, well, you could very easily make a lot of arbitrage. So if you know here that at time point 1, you observe this process to be slightly above 0, which happens with probability 1/2, then of course you're going to keep the stock and make a huge profit. And if it's slightly below 0 here at time point 1, then of course you're going to sell it immediately and just have only a very small loss. So this can be formalized, for instance, in this optimal stopping problem. So if you have this optimal stopping problem for X, then this has the value 1/2, but this optimal stopping problem for Y, of course, because it's a martingale, simply has the value 0. But this example should emphasize that there's a bit of a mismatch between this topology of weak convergence and this Wasserstein distance, which arises from optimal transport, and this temporal decision problem. So these kinds of aspects of temporal models which we're interested in also in financial contexts. And adapted optimal transport is basically a way to remedy this and similar issues. And to introduce adapted optimal transport, let us quickly look at what goes wrong for normal optimal transport. So what normal optimal transport does in this example is basically to say, okay, here we have a path which goes up, and we match this with this path here which goes up. Here we have a path which goes down, and we match this with this path which goes down. This defines a coupling between these two models. But of course, if we look at this mapping here, this match here a bit more precisely, this actually means that this point here, if we look at this point here at time point 1 for Y, then this point here is either moved slightly up or slightly down. And the decision whether to move this up or down depends on this value of Y at time point 2. So if Y has value 1 at time point 2, then we move this point up at time point 1. And if it has value -1 at time point 2, then we move it down at time point 1. So in other words, this transport rule for this point, which of course sits at time point 1, this depends on the future. And yeah, very intuitively speaking, adapted optimal transport just says that this is not the property which we want to have. We want these transports at earlier time points to actually be independent of the future. To make this mathematically, this means that under this coupling pi, it does not hold that x1 is conditionally independent of y2 given y1. And to define adapted optimal transport, we simply say the couplings that we look at should satisfy such a conditional independence criterion. So this is the definition. So for two marginals, nu and nu, and the coupling pi between them, and x and y distributed according to pi, we will say that pi is causal if here this, let's call this the past and the present of y up to time t, is independent of the future of x conditioned on this past and present of x. So this is when we call such a pi causal, if this holds for all t. Anti-causal is basically the same condition, but just we interchange x and y. And bicausal is the condition if we say that both causal and anti-causal condition hold. And now, to define this adapted optimal transport problem, we basically just replace the set of all couplings by the set of these causal, anti-causal, or bicausal couplings. And because this doesn't make a big difference for the results, which I will show you, I just use this placeholder here, which this bullet here for this set of couplings. So that means it's just one of these three options. And then this adapted optimal transport problem, this is given here. So again, I just use this notation with the bullet here. And it's the same as the normal optimal transport problem. We just replace this set of all couplings by the set of adapted couplings, which includes this independence assumptions for the past and the future, so to say. And the adapted Wasserstein distance is a particular case where we use, for this talk, without loss of generality, just the L1 distance as the cost function. And here, for the adapted Wasserstein distance, we always use the bicausal couplings because this is the symmetric option, and we want this to be a metric. And here I will show you some results from the literature. So in contrast to the normal Wasserstein distance, this adapted Wasserstein distance it's again a metric, but it's no longer compatible with the topology of weak convergence, but it's compatible with the adapted topology. Another desirable property of this adapted Wasserstein distance is that the stochastic processes actually form a geodesic space under this metric. Further, there are a lot of continuity or stability results in mathematical finance, for instance, of pricing and hedging problems in multi-period models. But of course, this adapted optimal transport has a lot of further applications. Basically, whenever a setting has a temporal component included, then this adapted optimal transport has shown to be a useful tool. So what I hope I could do with this short introduction was to convince you that this adapted optimal transport is an interesting and powerful tool for multi-period models or just distributions of time series in general. And the goal of our work by Gudmund and myself was really to make this problem feasible to work with in practice. So we wanted to actually calculate these problems numerically and give a toolbox to do so. There has been some previous literature on these problems, but they're mostly concerned with discrete problems in certain situations. And the goal of our work was really to provide a more general foundation for working with these adapted optimal transport problems numerically. So among others, if you followed optimal transport, then or it's my opinion that a lot of the success of modern optimal transport is based on regularization. So regularization is basically one of the backbones of fast computation of optimal transport problems. And we want to basically introduce the same kind of regularization also for adapted optimal transport problems. We also want to show that you can approximate continuous adapted optimal transport problems by discretization. In the paper, we also give a linear program formulation. This is not included in the talk here. And then finally, we introduce a variant of Stinkhorn's algorithm for the entropically regularized adapted optimal transport problem. Again, this is a very popular algorithm for normal optimal transport problems, and we want to also provide this tool for these adapted problems. Okay, so let me first show you the regularization for adapted optimal transport. So regularization basically just means we introduce this regularized problem, which is exactly the same as the normal adapted optimal transport problem. All that we're doing is we're adding this term, and this term is just epsilon, which is a positive but small constant, times the F divergence of this coupling pi, which we optimize over with respect to the product measure of the marginal. And of course, such an F divergence is a strictly convex functional. So this makes this objective here a strictly convex function in pi. And just intuitively speaking, strictly convex is, of course, nice to work with numerically. Of course, the first thing you want to know if you introduce such a regularization is that if you take epsilon small enough, whether you actually approximate the initial problem. And this is what we show. So this is the first theorem here. So if, of course, we have sufficient regularity, both of the marginals and of the cost function, then this approximation, at least of the optimal values, actually holds. And the same also holds that if any limit, we have some limit point of the optimizers of the regularized problems, then it's also an optimizer of the unregularized problem. I want to shortly mention that, of course, this result has its counterpart for normal optimal transport, but it's actually interesting that the method of proof for normal optimal transport was not applicable here, because it's basically some kind of block approximation there. And this does not work together with these causality constraints. So we actually found a novel method of proof here. And it's interesting that this method of proof can also yield here convergence rates in epsilon. And these can actually be shown to be sharp. And this is what Marcel Nutz and I did together in a paper last year. Okay, so this is regularization. So we've shown that regularization can be applied for these adapted optimal transport problems to approximate the unregularized problems. Next, I want to talk about discretization. So of course, usually we're interested in continuous models. So think of continuous time, on discrete time restrictions of something like Black-Scholes models or Heston models. Then of course, these distributions will not be finitely supported. So in practice, we usually require then a discretization step. But of course, to apply discretization and to approximate then these continuous problems, this implicitly, of course, requires a certain continuity of our problem. So the problem from marginals towards this objective function at least needs to be continuous in a suitable sense. Again, we show such a continuity in the paper. And the interesting part of this continuity is that we need here the topology on the marginals to be the adapted topology. So if the cost function is bounded and mu n converges to mu and mu n converges to nu, both in adapted topology, then actually here these measures can approximate this continuous problem. So of course, mu n and mu n usually should be thought of as some kind of discrete approximation. I just want to shortly mention the same holds true also if we look at the regularized problem here. Also, we can, of course, also deal with unbounded cost functions. But the most important comment I want to shortly elaborate is that using the adapted topology here in the marginals is really necessary. So if you just have an approximation there on the marginals in the topology of weak convergence, then this is not sufficient to yield continuity here of this problem. But luckily, these adapted approximations, so if you have a general continuous model here, mu and nu, then you actually can approximate them in the adapted topology. This was recently studied by the group in Vienna, so Julio Backhoff, Matthias Beigelberg, and so on. And yeah, so this is really applicable in practice, such approximations. Okay, and now the last part of these theoretical results, I want to show you this adapted version of Synchron's algorithm. So this is an algorithm which can calculate this regularized adapted optimal transport problem for a particular regularization. And this particular regularization is when this F divergence is given by the relative entropy or Kullback-Leibler divergence. And in this case, we also call this adapted problem, this regularized problem, the entropic AOT problem. So we want to find an efficient algorithm to solve this. And without loss of generality, or for this talk, let's just say for simplicity, we look at epsilon equals to 1. So what we're interested in is finding the optimizer, pi star, of this problem, which is just this adapted entropic AOT problem with epsilon equal to 1. And what we do here in this equality is a standard reformulation, which is known from normal optimal transport, which basically puts this cost function into the reference measure here of the relative entropy. And what this does is basically it shifts the viewpoint of the problem. So now we have some distribution pi 0, and we want to project this distribution pi 0 onto the set of couplings here. And this projection is under this relative entropy distance. So for the algorithm, this pi 0 here can be seen as the initialization. And then the idea of the algorithm is that this projection onto this set of couplings is split into two parts. So we write this set of couplings as the intersections of two sets, Q1 and Q2, where Q1 only fixes the first marginal and Q2 only fixes the second marginal. So the precise form depends on this choice for the bullet here, but for instance, for the bicausal problem, yeah, it would look like this. And just the important thing is the idea of the algorithm, because the idea is then, okay, you start with pi 0, then you project this pi 0 onto pi 1. The resulting measure you project onto on Q1, and then the resulting measure is projected onto Q2. This resulting measure is again projected onto Q1, and so on. And now the first thing you have to say about this is that this actually defines an algorithm. So you may wonder, okay, our goal was to solve some projection, and now this algorithm, these are just some other projections, but these are actually significantly easier. So each of these problems actually has a closed form solution. But now, of course, the more interesting question is, okay, similarly interesting question. So we know it's an algorithm, so we can compute these iterations of the synchron algorithm. The second question is, does it actually converge? And the answer is yes. So if this is this f of pi is just the objective value under some measure pi, this pi star is the optimizer of the entropic AOT problem, and pi k are the synchron iterations, then if the cost function is bounded, actually both the objective values and the log densities of the optimizers or of the iterations converge to the optimal values. And these actually converge exponentially here if the cost is bounded. If the cost is unbounded, we at least have qualitative convergence in certain settings, so for causal and anti-causal problems, but not for bicausal problems, interestingly. Or at least we don't know for bicausal problems. I just want to shortly mention, so the proof is based on the idea by Carlier for bounded cost, and for unbounded cost, it's based on stability considerations. So now what we basically did, okay, we introduced regularization, we introduced an algorithm to solve the regularized problem. And now in the numerical experiments, among others, we want to, of course, see, is it actually useful in practice, this algorithm? So first in the numerical experiments, I want to shortly show you this discretization thing. So, so this mu is now a discrete time Brownian motion, and maybe only look at the right-hand side. Here, the main thing I want to emphasize here is that you really need to approximate this mu with an adapted empirical measure. So with an approximation in the adapted topology, and not just with some empirical measure, because these will actually converge to different values. So here in the x-axis, you have the increasing amount of sample points that you use to approximate this continuous measure. And of course, here, this orange one converges to the true value. This is our result. But here, the blue one, if you just use an approximation in weak convergence, then this doesn't converge. So this is basically the first takeaway for these continuous problems. You actually need to use an approximation in adapted topology. Now, second, in this example, I want to illustrate that this adapted version of Synchron's algorithm actually yields good results in practice. So to visualize that, we choose mu and nu as just randomly chosen Markovian trees, so some random marginals. And basically, NB measures is a parameter for the size of these marginals. So think of if NB gets larger, then basically you're getting more and more continuous for these marginals. And here I showed some computational times for these, for calculating such an adapted optimal transport problem. So either the causal problem or the bicausal problem for different sizes of the marginals and with different methods. So and basically what I want to emphasize most is that if you choose the synchron algorithm and you choose a large epsilon, then you have very fast computation times at the cost of some, well, relatively small accuracy losses compared to the unregularized problems. But of course, you can choose epsilon larger, and then you get very small regularization errors. But you're still somewhat faster than the other methods based on linear programming and backward induction. I want to shortly show that this trend actually extrapolates. So if you choose even larger marginals, this backward induction was the best methods. If you didn't choose Synchron, then this Synchron actually yields much faster computation times for these very large problems. And now finally, in the last minutes, I want to briefly show you some numerical results regarding the geodesic properties of this adapted Wasserstein distance, because I think it's very interesting. This paper by Bartel, Beigelberg, and Pammer shows that this adapted Wasserstein distance can be used to define weighted averages of martingales, and these weighted averages actually retain the martingale property. So as an example here, in a very simple case, so here on the left-hand side, this would just be a binomial model. Here, this would be a trinomial model. And here on the right-hand side, you see a weighted average. This is basically 2/3 binomial model and 1/3 trinomial model. And what we know for this average is that it is both a martingale and it's Markovian. So that it's a martingale actually follows from this paper by Bartel, Beigelberg, and Pammer. And actually quite recently, together with Patrick Keridito, we show that it's also a Markovian, at least for almost all lambda. And of course, these two properties seem quite natural and of course important. If you take the average of martingale models, of Markovian martingale models, of course you would expect, I want a martingale model again, which is Markovian. But actually, if you just use the standard Wasserstein distance to define these averages, then your interpolation would satisfy neither of these properties. Okay, and finally, I just want to show you one instance which is a bit closer to, let's say, real-world models, but of course still quite toy models. So you have here CRR-type models with time-dependent variance. So you start with 3 models, x1, x2, x3, which have a different time dependence in their variance. And then you can take this barycenter with respect to this adapted optimal transport. And then you see here, okay, the barycenter has somehow smoothed out variance across time. Okay, and that's already it from my side. So yeah, I wanted to motivate this adapted optimal transport problem for you. Then I showed that you can use discretization to approximate these continuous problems as long as you use the adapted topology. Regularization can be applied and the regularization error can be controlled. Entropic regularization in particular allows for an adapted version of Synchron's algorithm, and this can actually yield significant speedups compared to other methods in practice. And I also showed that these geodesic properties of adapted optimal transport look quite promising numerically for the use of ensemble methods of different martingale models. So that's it for the talk. Thanks a lot for the attention.
Thank you very much. Okay, are there any comments or questions from the audience? As usual, you can type them in the chat or raise your virtual hand. Not yet. You mentioned earlier some sort of linear programming discretization approach. Can you say maybe a bit more what you sort of looked into that?
Yeah, so I mean, this basic problem, so this adapted optimal transport problem, if you don't have these causality constraints, then it's well known that this optimal transport problem, if you have discrete marginals, then the problem is again a linear program. But basically the question is, okay, these causality constraints that you introduce for this adapted optimal transport, the question is whether these constraints are actually also linear. And I mean, I'm not sure if this wasn't known, but at least it wasn't written down anywhere. So we also showed that these additional constraints, these causality or bicausality constraints for discrete marginals are again linear. So the resulting problem is still a linear program. But again, as shown here in this in these examples, if you simply implement this linear program, then the computational times get quite long. So yeah, it's a method, but it's maybe not the most efficient one.
Okay, great. Thank you very much. There is another question in the chat. Chito, do you want to ask yourself, or should I just read it out? So then I read it. The question is, do you see any relevance of independence problem approximation theory can be applied?
Sorry, could you say the first part again?
Do you see here any relevance of independence problem approximation theory can be applied?
So I'm not familiar with independence problem theory. Or maybe
I mean, I'm not sure. Chito, do you want to clarify the question?
Yeah, I'm sorry. Maybe it's relevant, but I'm just not familiar with this theory to give a good answer. Sorry.
Yeah, no problem. Okay. Are there any other questions or comments? No, if not, then yeah, thank you very much again, Stephan, for this very nice talk.